Welcome to Empowered Learning. This video will be about solving second-order Euler-Cauchy equations. So when we talk about Euler-Cauchy equations, what we're really talking about is another special case of a second-order linear homogeneous type of equation. If you've watched my videos on solving second-order linear homogeneous equations, where all of the coefficients are constant, then you'll realize here that the form of the equation that I have here is actually what that looks like. Okay. Now, the Euler-Cauchy equation is similar in that it still has the same profile of we have the second derivative term first, then the first derivative term, and then the term with no derivative, and then it equals 0. The thing that is different, though, is that not all of our coefficients here are going to be constants any longer. Okay, specifically, this alpha and this beta here will be functions of our independent variable, which we're normally going to call x. Sometimes we'll call it t, but we'll just assume for simplicity x now. So alpha and beta will be a function of x, whereas gamma here will actually be a constant. And so I'm going to scroll down here. So as you can see here, we have, this is technically a coefficient of our equation. This is technically a coefficient, and this is technically 1. But you see here alpha and beta are actually functions of x, where gamma here is actually still a real number constant. And so these equations that are in this form are what we call Euler-Cauchy equations. They're also known as Cauchy-Eulers, or just Eulers, or in a more general term, equidimensional type of equations. Now, the reason why they're called equidimensional type of equations is because, as we can see in this term, notice that the power that x is raised to is the same number as the order of the derivative. Okay, and each term has that quality about itself. So you can see here that a Cauchy-Euler equation in its standard form is going to look like this, where we're going to have some function of x, where of course this will be basically number x raised to 2, number x raised to the 1, and then of course this could be like number x raised to the 0 if we wanted it to be that way. Okay. Now in general, if we had an nth order Euler-Cauchy equation, of course it will look like what you see here. Okay, and again, this is in its standard form. Okay, standard form. There are other forms of these types of this type of equation that you'll actually see, and I'm going to write one here. So another way that you could rewrite this is basically just taking this equation here and dividing both sides by x squared. Okay, where x here is understood to not be able to equal 0. And that's very important to know here, because if we allowed x to equal 0, then this whole term here would go away, and we would no longer have a second order linear equation anymore. So one of the conditions for this equation to be in the classification that it is that x can never be equal to 0. All right, so anyway, if we go ahead and divide everything by x squared on both sides of this equation here, what we're going to end up with is something that looks like this. So we'll have a y double prime plus b divided by x y prime plus c divided by x squared y, and then that equals 0. This is another alternative form of an Euler-Cauchy equation. Okay. Now, we will also see some Euler-Cauchy equations in other forms other than these two. Okay. The main thing to check whenever you're trying to see if an ordinary differential equation is an Euler-Cauchy one is to say, does each term have that equidimensional characteristic to it, or could I manipulate the equation so that if needed to, I force it to have that equidimensional characteristic to it? Okay, and I will do an example of that so that you can see what that looks like. Now, with these types of equations, just like how, if you watched the video for the second order linear homogeneous ones, where all the coefficients are constant, one of the things that we needed to do is to identify a general solution, so that way we could kind of figure out, all right, well, what are going to be the special cases of my general solution? And so this type of equation has the same flavor as a second order linear homogeneous equation, where all the coefficients are constants. And hopefully, as you see me go through this presentation, you'll see how it's very similar. So the first thing that we need to do is figure out what a suitable solution is going to be. And it just so happens that a suitable solution for these types of equation, this type of equation is a power function, mainly x raised to the r, where r can be some real number or complex number. Okay. So if we move forward here, I'm going to show you why it is actually a solution to this equation type. So if we assume that this is going to be a solution, then of course we take the first and second derivatives here. And notice that it's very easy to take the first and second derivative of a power function. And because of that, one of the things that we're going to see a little bit later is that although we will have what we call an indicile equation, is basically a fancy name for a characteristic equation for this equation type. Although we're going to have that, we really don't need to memorize the corresponding characteristic for this equation type, because what we have to do to actually get what the actual characteristic equation will be is relatively easy. And again, I'll show you that as well. So here, in verifying that this is actually a solution, we take our second derivative, which is what all this is, plug it in, first derivative, all that is plug it in, and then of course our original function. And after we do some algebraic manipulation and such, you'll see here that what we end up getting is a situation where we have this particular expression multiplied times x raised to the r. Okay. Now, we know that x raised to the r can't equal 0 because we know x can't equal 0. So in order for all this to be true, it must be true that this particular expression here has to equal 0. Okay. And so just like with the second order linear homogeneous equations, where all the coefficients are constant, what this ends up being is your characteristic equation. Okay. And so if you notice here, I've written the characteristic equation in 3 different ways. Okay. And really it's 2 different ways, where here I'm just taking this b minus a and letting it be big A here, c divided by a, letting it be big B here. Okay. So the 2 most common forms of this second order characteristic equation that we use is equation 1 or equation 2. You are going to see me use this version of this characteristic equation the most, as a matter of fact, all the time, because of the fact that it's so similar to the characteristic equation for a second order linear homogeneous equation, where all the coefficients are constant. Notice here, and of course we can call it a LCC-ODE for short, so linear constant coefficient ordinary differential equation, second order. And so that's what that acronym means here. So if you notice, the only thing that's different in between this characteristic equation and this one is that this b now is b minus a. So that's the reason why I like to use this one. But I know I have seen this form used and this form used as well. So now that we kind of understand, well, hey, all we need to know is what this characteristic equation is that's for an Euler-Cauchy type of equation. If I can figure that out, then I can figure out what my solutions look like. And that's exactly what we're going to do here. Now, I do want to have a quick discussion about this characteristic equation. And with Euler-Cauchys, to be proper, we do not call it a characteristic equation, even though we can. Okay, what its actual name is an indicil equation, and it's not important at this point that you necessarily remember that. If you can keep different names straight in your head, it would be nice to do so because it may help you out later. But in short, part of the reason why it is called an indicil equation versus a regular characteristic equation is because Euler-Cauchy equations are actually the foundational basis for being able to solve ordinary differential equations via power series technique called the Frobenius method. And in that method, one of the things that we have to find out when we deal with the power series is the lowest quote unquote index that we need to use so that we can find out what our coefficients are going to be in doing that method. So it turns out that this particular characteristic equation for the Euler-Cauchy is tied to us being able to find out that lowest index so that we can mathematically manipulate those types of equations to be able to solve them using power series techniques. And so that is why it's called indicil. So indicil, you can think of it as a fancy word for index, okay? And so that's why it's named that. And that's why you'll hear me say it throughout this video here, because even though it is essentially a characteristic equation, the foundational use for it at a higher level makes the word indicil be a little bit more appropriate. Okay. All right. So moving on here. So now that we know that x raised to the r is a suitable solution here, what we're going to do is look at, well, what happens for the case, for all the different cases here. Okay. All right. Yep. So let's get this here. Yep. All right. So if we solve this particular indicil equation for r, of course, depending upon what r looks like, that's going to also let us know what our general solutions to this equation type looks like. Okay. And so we're going to go through that now. So one thing I want to mention before we actually get into that is, again, with the indicil equations for second order, this only goes for a second order Euler-Cauchy. Okay. If we have a third order Euler-Cauchy, then the indicil equation is going to look different. If we have a fourth order, it's going to look different. And so my point here is that I made the comment earlier that we have y equals x raised to the r as a general solution, and it's very easy to take the first derivative, second derivative, third derivative of this type of function here. And normally, let's say if we have to deal with a third or fourth or fifth order Euler-Cauchy, instead of trying to remember what is the fifth order indicil equation to use, we just take all the derivatives and dump everything into the ODE and just work it out. Because in doing that, that's actually more efficient than trying to remember, hey, what's the fifth order EC or Euler-Cauchy indicil equation. Okay. All right. So here is our indicil equation. Here's what it looks like if we plug this into the quadratic formula. And of course, the main thing that we're concerned about here is, what is this discriminant going to be? Is it going to be positive? Is it going to be 0? Or is it going to be negative? And so just like with the linear constant coefficient ordinary differential equations of second order, depending upon whether the discriminant is positive, 0, or negative, also depends upon what the general solution looks like. Okay. Now, of course, the easiest case, just like it was for the second order linear homogeneous ones with the constant coefficients, if our discriminant is positive, then we know we have two distinct real number values. And so that means that we can just do a linear combination of these two functions here, where R1 and R2 will be two distinct numbers. So our general solution for an EC equation, that's going to be abbreviation for Euler-Cauchy, is going to be looking like what you see here. Okay. And again, that's just C1 times x raised to the first solution plus C2 times x raised to the second solution. For the case 2 situation, this is when our discriminant is 0. And of course, when our discriminant is 0 here, just like what we had before, if you remember for the second order linear homogeneous ones where the coefficients were always constant, when our discriminant was 0, we had, I shouldn't put x here, but we had r is equal to negative b over 2a. Of course, our b now for this equation type is b minus a. So that's why we have r is equal to negative b minus a over 2a. Okay. And it turns out that in doing this, we have a double root. And so what that means for us is that we only have one bona fide solution that we know of, but we need to find another one since it's a second order Euler-Cauchy. And so we can do reduction of order to be able to find the other one, just like how we did reduction of order with the second order linear homogeneous equations with the constant coefficients to find out what that second solution to complete the basis would be. Okay. So I'm going to quickly take you through this process. The end result of this is that we're going to find that our u is going to end up being natural log of x. Okay. Because again, if a reduction of order says if we have a solution y1, then y2 is just going to be u times y1, where u in this case is going to be a function of x. And so we go through this whole process. We're essentially going to come here and say, all right, well, if we assume that y2 is going to be a solution that looks like this, we need to take the first and second derivatives of it. Okay. And so that's exactly what I do here. So if y2 is equal to this, then I'm going to take the first derivative of y sub 2, and that's what this is going to look like. And then I take, that's what it looks like, but then we finish it up here. And then we take the second derivative, okay? And we take all that information and we dump it into our original ODE here, okay? Now, I'm kind of skipping through the math relatively quickly because it's not as important for you to know every little step in this process, but I do want you to get an idea of how we actually get these solutions. And I also want you to see that if you've been watching my videos that are previous to this, I want you to see how all the equation solving techniques that we have learned earlier are also being used to help us now. So we're leveraging what we've learned before to be able to help us to move forward now. So we dump all this information, what is y sub 2 double prime, y sub 2 prime, y sub 2, into our corresponding ODE. And then, of course, we're going to do some rearranging here. In the reduction of order process, one of the things that we expect to happen is that all of these terms here And I'm picking these because out of all the terms, these are the terms of lowest order in terms of derivatives are concerned. Okay. And we expect all of these to go to 0. Okay. We expect all of them to go to 0. So I'm going to show you why that is now. So if we put this together here, notice that once we do a little simplification, we have a times r minus 1 plus br plus c. And all of that, we could rewrite it this way. Okay. Now, if you notice, this was one of the forms of our indicial equation. And if I write it out, this will be ar squared minus ar plus br plus c. And all that times u equals 0. And here, notice that this middle part here, this is just b minus a times r. So what we have here is essentially our indicial equation, our indicial expression, times u equals 0. And so we know by definition of the indicial equation, all that has to be 0. Okay. So that's how we know all these terms end up going to 0 here. So once we do that, then it's just a matter of dealing with all of this equals 0. And we're going to figure out that, hey, we can simplify this some more. So we have the situation here. And once we simplify it, we get to this point. And just like how we did with the second order linear homogeneous equations with the constant coefficients, I know that's a lot to say, we know that our r in the case of case 2, whenever our discriminant is 0, is a minus b minus a all over 2a. And if I take that and I actually plug it into here, and you're going to see where I do that. So down here, where I actually take that and plug that into here, I see that what I get as a result is just going to be a. Okay, so 2a times r plus b, and I let r be a negative in parentheses b minus a over 2a. What I just end up getting is just a. Okay, and if I get that, then this is the corresponding equation that comes out. And where these v's came from is that up here, I went ahead and decided to reduce the order of this equation by 1 by making a substitution. And of course, this is, again, part of the reduction of order process. So by doing all that, what I notice here is that I end up with what I recognize to be either a first order linear equation or a separable equation. Okay. It can be separable because I could rewrite this where everything in terms of x would be on one side, everything in terms of v would be on the other. It can be linear because this has the form of a standard first order linear equation. But normally when we talk about linear, this particular expression here is not 0. Okay. But a separable equation is really just a first order linear equation where this right hand side term is 0. That's really all it is. Okay. Now, at this point, we are happy because we know, hey, I know how to solve that. Okay. So now we just kind of go through the whole process of trying to solve. Okay. So again, I'm not going to spend too much time on this, but if I go through this process here, you'll see that a lot of this looks familiar. What we end up getting, which is the important part here, is that u is equal to some constant times natural log of absolute value of x plus another constant. Okay. And those absolute value signs I can drop here because of the fact that we're going to assume that x is going to be greater than 0. Okay. Now, in general, we would leave it in this form here with the absolute values, but in actual applications, a lot of times, not always, but a lot of times, we're only looking at independent values that are greater than 0. So it's customary to go ahead and drop the absolute value there. If we were modeling a situation where, let's say, x was position, and we needed to look at position to the left of a reference point and to the right of one, then of course we would leave the natural log in. Other than that, we normally deal with what we call right-sided type functions. So in that instance, we can drop the absolute values. Now, out of this, these constants are not important. What is important is the root function, which is natural log of x. And so in this instance here, we see that our u ends up being natural log of x. So what that means here is that our second solution that completes our basis is just going to be y1, which is x raised to the r, times u, which is natural log of x. And so just like with the second order linear homogeneous ODEs with the constant coefficients, if we had, let's say, e raised to the rx as the only solution that came from the characteristic equation, then of course we had x times e raised to the rx as our second solution that came from reduction of order. Okay, so in this instance we end up having x raised to the r as that first solution, and then of course x raised to the r times natural log of x as the second one from the reduction of order process to complete our basis of solutions. And then of course here we know that if we take linear combinations of these two functions, then we can basically get a general solution to this Euler-Cauchy equation for case 2. And so again, you could express it this way or you could express it this way. Now for case 3, if you remember from the second order linear homogeneous equations with the constant coefficients, the third case is when we had the complex conjugate roots for our characteristic equation. And it will be no different for our indicil equation here. We're going to end up having complex conjugate roots because our discriminant for this equation type here will be negative. Okay. So of course, that means we need to identify what our real part and what our imaginary part of these complex conjugates are, because that's what's important to us. Okay. In general, the solution to this equation type is going to be y is equal to x raised to the lambda plus or minus omega I. And of course, this is a complex number here. Of course, if omega is 0, then it collapses to a real number. Okay? And if lambda is 0, then it collapses to strictly an imaginary number. Now, again, the important thing here to know is that although this is technically a solution, it is not a useful one because, again, we use these Euler-Cauchy types of equations to model real valued situations. So we're going to have to do some slick mathematical manipulation to get some general solutions that are all real valued, just like how we did for the linear constant coefficient ODEs of the second order. Okay, so here how we kind of work our magic on this is that, first of all, we realize that since this is x raised to a complex number, but this is still following exponential rules here, we could rewrite this as the product of real part and imaginary part. Okay, where this real part here is x raised to the lambda, and we have x raised to the plus or minus omega I for the imaginary part. We also remember that e raised to the natural log of x is just equal to x. And so if we replace x with this expression here, like what you see me doing from this step to this step, then what you see is that we essentially have Euler's relation here. Okay. Now I know this looks a little weird here, but all of this is basically being multiplied times each other. So if I was to rewrite this in a different way, this would, well, first of all, let me sort of explain what's going on here. So when we make this substitution here, e raised to the natural log of x, right here, notice that we actually have the following. So we have e raised to the natural log of x, and then all of this is being raised to this power, okay? So this is following the same rule here as a raised to the m, all that raised to the n. And of course, here we can multiply the exponents. So that's what's going on here. So if you look at it in that sense, then if I rewrite it this way as e raised to the plus or minus, and then here omega times natural log of x, all in parentheses, and I put the I on the outside, then of course this looks a little bit more like this plus or minus I raised to the theta here, where of course theta is going to be all this business here, okay? So it looks funny, but it works. And so that's why I say here that what we see here is actually this, where our theta is going to be omega times natural log of x. And again, if we take Euler's form, Euler's formula, and then the conjugate of that, and we see that from here we would actually have two valid solutions. Okay, if we just replace the e raised to the positive I theta with this, and then of course we did it with the minus I theta, it would be that. These would be two valid solutions. But again, these two solutions aren't very useful to model it with real value things. So what we're going to do is borrow what we did for the linear constant coefficient ordinary differential equations of second order. Is we essentially said we're going to add these two solutions here together to come up with another solution. And we're also going to say I times the difference of these two solutions here to come up with a different solution, okay? Because remember, if we have any two solutions, we can do any linear combination of them to come up with another set of solutions. And so to make a long story short, we do all that business, and what we end up with is a situation where when we add the two complex solutions together we originally got, we end up getting this term. And when we do I times the difference of them, we end up getting this term. And of course, our general solution here is just going to be a sum of these two. And since they both have x raised to the lambda in those terms, I'll just go ahead and factor that out. And so this is what our case 3 would be. All right. So now we're going to go through a summary of everything and then do some examples. All right, so the summary here, we have this second order Euler-Cauchy equation. Remember that Euler-Cauchy equations are equidimensional equations because each term, the coefficients, the order of the coefficients and the order of the derivatives are the same, okay? And here in general, a suitable solution would be x raised to the r, where x can be any real number other than 0. And we are going to determine what r is by what we call our indicil equation. Remember, that's our fancy way of saying that we have a characteristic equation for this equation type. And if you remember, we have three different ways of expressing this particular indicial equation. When we first encountered this, we saw it in this way and this way. And whenever we went through the reduction of order process, we actually saw it this way. Again, personally, I will be using this form in this video just because, again, it is very similar to the characteristic equation for a linear constant coefficient ODE of second order, okay? And here, of course, I identify what the discriminant looks like in both of these cases, if that's something that is of importance to you. All right, so now that we know what our indicial equations are, or the choices for them, we know that case 1, our discriminant is greater than 0. We end up with two distinct real number value for the solution to the indicial equation. And we see there's just a linear combination of x raised to the what those solutions were. For case 2, that's the one where we had the double root. So we had to do reduction of order. We knew x raised to the r was a solution, but doing reduction of order also gave us x raised to the r times the natural log of x. Okay. And if we do linear combinations of these, have our solution here. Now, I threw this note in just because it is useful to use if you have to deal with higher order Euler-Cauchys. So if we had a third order Euler-Cauchy, then, and it was of this particular type, a case 2 type, then of course we could come up with a general third order indicial equation, a third order general solution by basically doing this. So you could think of this term here as the x raised to the r times natural log of x raised to the 0 term. This one could be x raised to the r times natural log of x raised to the 1 term. And this one is x times r times natural log of x raised to the 2. Okay, and notice that we stop here one order short of what the actual order of the equation is. Okay, and so in general, and I don't know why this says this, this should say n minus 1. So that's what it's going to be in general. Okay. All right, and of course for case 3, instead of having C1 cosine of omega x and sine of omega x, now we have cosine of the product of omega and natural log of x for inside both the cosine and sine functions. Everything else pretty much the same. All right, so let's get to doing some examples. So for the case 1 examples, the first thing we want to check out is that we actually do have a second order Euler-Cauchy. Notice that we have the equidimensional thing happening here. This is an understood 1. This is the same as y prime. So we got the equidimensional thing happening here. And of course, we have no derivative here. So this number here is like having something raised to the something times x raised to the 0 power. Okay, so we know this fits the bill for second order Euler-Cauchy. Our indicial equation is just a r squared plus b minus a times r plus c, where in this case our a, remember our a is just going to be a real number coefficient here. And so it's just going to be 1 in this case. So a is 1, b is going to be minus 2, and c is going to be minus 4. Okay. Again, do not mistake the fact that this is the actual coefficient for the coefficient for the indicial equation. The indicial equation, the coefficients can only be real numbers. Okay. So once we put all that in, then of course it's just a matter of plug and play. We see that we get r squared minus 3r minus 4. That easily factors to r plus 1 times r minus 4. And if we set both factors equal to 0, we see that -1 and 4 are our roots for the indicial equation. So our solution is just going to be constant times x raised to the -1 plus constant times x raised to the 4. And of course, we could rewrite it this way. And that's pretty much all there is to this equation type. Now, depending upon what you get from the indicial equation, the factoring may get a little interesting, but other than that, everything else pretty much is the same. So for the next example, kind of the same thing here. So notice that in this equation, it is a second order Euler-Cauchy, but notice that there is a term missing here, okay? So notice that we have a plus 0x y prime term minus 20, and I'm going to write this x raised to the 1, and this is 20x raised to the 0 y, okay? And so this is actually what it would look like if we spelled out everything, where again, this is 0 times x raised to the 1 times y prime. So degree of 1 here, first order or first derivative here, that matches. So this is technically an Euler-Cauchy of the second order. So indicial equation is the same. Here we see that our A is 1. Our B is 0 because that's where it is here, and our C is minus 20, okay? So from there, again, we just plug everything in, get it into this form, factor, figure out what our roots are, okay? And again, not much to it. Once you know what the indicial equation what the coefficients you're going to plug into the indicial equation is, and you factor it out or use quadratic formula, you're pretty much good to go from there. So for our next equation, we see that going to pretty much do the same thing as we've done before. Our indicial equation is going to be a times r squared plus b minus a times r plus c equals 0. And of course, a in this case is going to be 1, b is going to be minus 3, c is going to be minus 21. So we go and plug in all that information. So this would just be r squared plus b minus a times r plus the c, which is a minus 21. So go ahead and take that off, equals 0. And so from here, this is just r squared minus 4r minus 21 equals 0. And if we factor out the left-hand side, this would be r minus 7 times r plus 3 equals 0. And of course, that just means that our solutions to this equation are just 7 and minus 3. So therefore, our general solution is just going to be C1 x raised to the first one, which we'll just say 7 here, plus C2 x raised to the second one, which will be the negative 3. This would be our general solution. All right, so for our next example, we see here that, again, we have a second order Euler-Cauchy. We see we have the equidimension characteristic happen in the first term, as well as in the second term. But notice that we don't have a third term, okay? So since we don't have a third term, we know that our indicial equation will have a value of 0 for the C value. So here from this, our A is going to be 1, our B is going to be minus 20, and our C is going to be 0. And that means that for our indicial equation, which looks like this, this value c here is going to be 0. So this will be r squared plus, and have a minus 20 minus 1, r plus 0. And this is just r squared minus 21, r equals 0. And of course, from here, if we factor out greatest common factor, we see we just have r times r minus 21, which this means that r is either equal to 0 or 21. And so therefore, because of that, our general solution here, I'll just write the general form here. And of course, R1 will be 0, so x raised to the 0, and R2 will be 21. And of course, this x raised to the 0 here, all that is just 1. So it just ends up being C1 plus C2 x raised to the 21 will be our general solution. Okay, so for our next example here, notice that we actually have a fourth order Euler-Cauchy equation. It's not a second order, so we're actually going to work an example like this one so that you can see that if we just take the successive derivatives of whatever, if we take the successive derivatives of x raised to the r, we can still come up with the indicial equation that we need to be able to solve this equation here, okay? Now, in saying that, notice that this particular equation is not in the traditional standard form of an Euler-Cauchy, okay? So notice here we do not have the equidimensional thing going on here, and we don't have it going on here, okay? However, if we were to take this equation here, and I'm going to rewrite it here. If we were to take this equation and then multiply both sides of it by x cubed, then what you would end up having here is x to the fourth derivative of y, plus 6x cubed, third derivative of y, equals 0. And this is the standard form for Euler-Cauchy. And of course, this would be of the third order. So even though this does not look like an Euler-Cauchy to begin with, it actually is. And so this is what I meant by checking to see if, number one, it is in the standard form, or number two, if we could force it to be in that standard form. Okay. So now that we know that this is an Euler-Cauchy, whether it looks this way or if it looks this way, we're going to go ahead and solve the problem with it looking this way. Okay. And I'm going to switch back to the notes so that we can do that. So since this, again, is a fourth order Euler-Cauchy, we are going to have to do this what I call the traditional way, which is basically find the successive derivatives of y so that we could sub everything in and figure out what our indicial equation is. So we'll go ahead and get started with that. So if y is equal to x raised to the r is a solution, then of course that means the first derivative is going to be r. It's going to be r times x raised to the r. And that's still messing up here. The second derivative, should be minus 1 here as well, forgetting that. For the second derivative, it'll just be this constant times whatever the exponent is, and then we subtract 1 from the exponent again, and we just keep doing that. So this next one here end up being this, and the fourth one, I'm not going to have enough room, so I'll just write it over here. fourth derivative here will be r times r minus 1 times r minus 2 times r minus 3 x raised to the r minus 4. And I'll go ahead and get that out. So now that we have this, we are going to substitute all of that into our original ODE here. All right, so therefore, we have x to the fourth. And of course, now we need the fourth derivative, which is going to be all this business here. And this is going to be plus 6 times x cubed. And now the third derivative, which is right here. And all that is equal to 0. Now, from what we see here, if I take this x to the fourth and I multiply it times this x raised to the r minus 4, the 4 and the minus 4, due to our exponent rules, will add together to be 0. So all I will end up having here is x raised to the r times all this business here. Okay. So because of that, I know that this next step is just going to be x raised to the r times r minus 1 times r minus 2 times r minus 3. Okay. And similarly here, if I take this x cubed and multiply it times x raised to the r minus 3, that's just going to leave us with x raised to the r. So here we have x raised to the r. And of course, this will just be 6 times r minus 1 times r minus 2. And that will equal 0. Of course, what we can do is divide both sides by x raised to the r, noting that x can't equal 0. And so if we do that, then we will just have r times r minus 1 times r minus 2 times r minus 3 plus 6r times r minus 1, r minus 2 is equal to 0. And from here, if we factor out like terms, and so we'll see here we have r minus 1, and r minus 2 that are like terms. So we can factor that out of both terms here. And if we do, we have r times r minus 1 times r minus 2. And we keep the r minus 3 in the first term. And we keep the plus 6 in the second term, equals 0. And of course, r minus 3 plus 6 is just going to be r plus 3. And what you see that we actually have here is our indecisional equation for this fourth order Euler-Cauchy equation. Now, it did take a little bit of work, but the work wasn't too difficult. And from this, the great thing is that we already have everything factored out. So we know that r is either 0, 1, 2, or negative 3. So very easy come up with. And we see here that since all of these are distinct, we automatically know what our solutions are going to be, because our basis of solutions is going to be x raised to the 0, x raised to the 1, x raised to the 2, x raised to the negative 3. This is going to be our basis of solutions. And so we can just do linear combinations of these. And so x raised to the 0, of course, is just 1. So our final general solution here will just be C1 plus C2x plus C3x squared plus C4x raised to the negative 3. And that would be our final answer for this particular equation. All right, so this will be our last case 1 example. And with this one, we see we have an initial value problem. Again, once we find a general solution, we just use the initial value problem, initial conditions rather, to figure out what the constants are. So again, since this is a second order Euler-Cauchy, we know that our indicial equation here is just going to be AR squared plus B minus A times R plus C equals 0. And this is where our A is going to be 1, B is going to be 3, and C is going to be 0 here because we don't have a term that just has Y in it. So we assume that it's going to be plus 0Y. So from here, that means that we have R squared plus B minus A, or 3 minus 1 is going to be 2R plus 0, or just leave that as 2R here. So we'll get rid of that. So this is equal 0. And of course, once we factor out the greatest common factor of R, we see that R is either going to be 0 or -2. And thus, for our general solution, this will be y of x. It's just going to be c1 x raised to the 0 plus c2 x raised to the -2, which would just be c1 plus c2 x raised to the -2. Because again, x raised to the 0 is just 1. So this is our general solution. So now that we know that our general solution is this, we can go ahead and take the first derivative, because we're going to need that for the initial conditions here. And of course, the derivative of any constant is 0. And the derivative of x raised to the -2 is going to be a -2 x raised to the -3. And of course, that constant c2, we have to keep that in there. So now we are going to look at our first initial condition. When x is 1, y is 0. So looking here, we see for our general solution here, which is this, we're going to let x equal 1, let y equal 0. So this will be 0 for here equals c1 plus c2. And then in place of x, we have a 1 raised to the -2. And 1 raised to the -2 is just like 1 divided by 1 raised to the +2. And all of this is just going to be 1. So from here, we see that c1 plus c2 is equal to 0, which is just another way of saying that c1 is the negative of whatever c2 is. So for our next initial condition, we're told here that we take the derivative, evaluated at 1, we get 4. Okay. So here for our derivative, we know that the left-hand side here would just be 4. This will be minus 2c2. This will be 1 raised to the -3. And 1 raised to the -3 is the same as 1 raised to the 1 raised to the +3, which is, again, still just 1. So this just means here that we have 4 is equal to minus c2, which means that c2 is a -2. And if c2 is -2, then from here that means c1 is going to be a negative of a -2 or +2. And so now we know what our constants are. So C1 is just going to be 2 plus, and so here I'm just rewriting this now, filling in the constants to get my particular solution. So y of x is 2 plus, and of course, that's a minus 2, so we'll go ahead and, all right, so C2 is a minus 2, and that's x raised to the negative 2. So this will be our particular solution for this equation. All right, so now let's get into some case 2 examples. And remember, case 2 is a situation where the discriminant is 0 for these Euler-Cauchy equations. And because of that, we just have one root that is a double root for the solution to our indecisional equation. And because of that, we have to use reduction of order. Well, we could use reduction of order, but since we already know what the result is going to be, we already know what the second solution is going to be. So for this particular equation here, remember that we have the equidimensional thing going on here. Remember, this is raised to the 1, and this is the same as the first derivative. And of course, with us having an understood 1 here, that would be the same as having x raised to the 0. And of course, no derivative here means order 0. So we see that everything matches. So here for the indecisional equation, this is what we're going to use. And of course, our A is going to be 4, B is going to be 8, and C is going to be 1. So 4, 8, 1. And then of course, in there we just plug everything in. We see that we get 4r squared plus 4r plus 1 is equal to 0. And this turns out to be 2r plus 1 quantity squared, which means that just 2r plus 1 is equal to 0, and thus r is just equal to a negative 1/2. And since that is the only solution to our indecisional equation, we know that this is going to be the situation with the double root. And thus our general solution here will consist of a linear combination of x raised to the r times x raised to the r times natural log of x. And so we see here that because of that, since r is a negative 1/2, then this would be our general solution in fractional exponent form, and this will be our solution if we write it in radical form. Okay, and notice here, since we're dealing with basically square root of x, and of course square root of x is in the denominator, we know that x has to be greater than 0 in this case, because when x is equal to 0, of course that's not allowed for the Euler-Cauchy equations, and when x is less than 0, that would make the denominator there complex. All right, so for our next example, we see that I've done the work here, but notice that this is not in the standard Euler-Cauchy form for second order ODE. So what we have to do here is see, can we force this to look like it's in its standard form? And of course, if I was to multiply both sides of this equation by x, then that would just end up being x squared y double prime plus x y prime equals 0. And of course, here we see the equidimensional thing going on here. That lets us know that this is indeed an Euler-Cauchy equation. So again, we use our indecisional equation formula here to find our roots r, which is basically going to be our exponents here. A is 1, B is 1, and C is 0. So we plug all that information in. And of course, B minus A, 1 minus 1, is 0. So that's why we have that here. And of course, C is 0. So that's why we have that here. So basically, r squared is equal to 0, which means r is equal to 0. So this is a double root. And once again, that means that we automatically know this is our general solution. And all we do is just let r equal 0. And we see we end up getting C1 plus C2 natural log of x, where C1 and C2 are constants, or real number constants rather. All right, so for our next example, again, we see the equidimensional thing going on here again. So we know that this is an Euler-Cauchy equation. Our indicial equation here will be a r squared plus b minus a times r plus c equals 0. And of course here our a in this case will be a 1, our b in this case will be a 5, and our c in this case would be a 4. So now that we have that information, we can go ahead and plug everything in. And when we do, we see we have r squared plus our b is 5, our a is 1. So 5 minus 1 r plus c, which is 4. So that's just r squared plus 4r plus 4. All that equals 0. And of course, if we factor that out, that would be r plus 2 times r plus 2. And of course, from here, we just know that r ends up equaling a negative 2. And since it's the only solution that we have, we know that in general, our solution is going to be C1 plus C2. Back this up here. So it'll be C1 plus C2 times natural log of x, and all that will be multiplied by x raised to the r. Or you could express it this way: C1 x raised to the r plus C2 x raised to the r natural log of x. Either way is fine. So here r is negative 2, so we just plug that in, and we are done. So that would be the general solution for this particular ODE. So for this next example, again, we see we have the equidimensional thing going on. Notice in this case here, we do not have a y prime term. So this, we got 0 y prime. So that's going to affect our indicial equation. So what this tells us here is that this is an Euler-Cauchy equation. Our indicial equation will look like this, where our a in this case is 4, our b is 0, because that's where the b comes from, the coefficient for the y prime term, and c is going to be 1. So from that, therefore, we have 4r squared plus 0 minus 4r, and then plus 1 equals 0. And then this is just 4r squared minus 4r plus 1 equal to 0. Of course, from here, if we factor this, we've got 4r squared, so that's 2r, and since we have minus plus here, we know this has to be minus minus, and of course the factors of 1 is just 1 in itself, and of course if we multiply all this out, we'll see that we indeed get 4r squared minus 4r plus 1. So this just tells us that 2r minus 1 is equal to 0, so that means r is 1/2. And again, double root. So therefore, general solution will look like this. And I'm going to keep it in this form this time so that you can see it. And so this will be C1 plus C2 natural log of x. And of course our r is 1/2. So that'll be x raised to the 1/2. And if you want, you could express that as just square root of x here. Okay. And so that will be the answer to this particular equation. So its general solution would be what you see there. Now, one thing we do want to keep in mind here is that since we're dealing with square root of x here, we know x would indeed have to be just greater than 0. And that's because we know x is not allowed to be 0 for any Euler-Cauchy equation. And we know that if x was negative or less than 0, then that would produce complex numbers. And that's not what we want here. We don't mind. We just don't want complex numbers here. We know it's a possibility, but we're trying to model real value things. So since we're trying to model real value things, we're not going to be entering in any numbers that will make our situations complex. So we'll go ahead and move on to our last example for the case 2 types of Euler-Cauchys. And so this last one here, we will have an initial condition or initial conditions that we'll have, so that we'll be able to actually find out what our C1 and C2 are. Okay, so for this example again, we check to see that we have the equidimensional thing going on. So therefore, we know this is an Euler-Cauchy. Since we know it's an Euler-Cauchy, then of course our indicil equation in general will be a r squared plus b minus a times r plus c is equal to 0, where a in this case is 9, b is 3, and c is 1. So using all that information and plugging it in, our indicil equation becomes 9r squared plus 3 minus 9r plus 1. That equals 0 here. And that will be 9r squared minus 6r plus 1 equals 0. And if we were to factor this out, what we would find out here is 9r squared. We can break that up as 3r. We got minus plus, we got minus, minus. And of course, the factors of 1 is just 1 and 1. And if we were to FOIL this back together, we would see that it does indeed equal 9r squared minus 6r plus 1. So this tells us here that 3r minus 1 is equal to 0, which in turn tells us that r is equal to 1/3. So from that, we know that our general solution here, because we only have one solution here, we know that this is a double root. So it's going to be C1 plus C2 natural log of x. All that times x raised to the r. And of course, our r in this case will be 1/3 here. So I'll go ahead and just write in the 1/3 right there. Okay, so that is our general solution. Remember that x raised to the 1/3 is the same as cube root. So I'm going to rewrite it that way because it may be advantageous for us to use it in that form, or maybe easier for you to picture what's going on in that form as we use this for our initial conditions. So notice that since we have two initial conditions and one of them contains the first derivative, we're going to go ahead and figure out what the first derivative is for this. And I'm going to use it in this first form here. So using the product rule, we'll take the derivative of C1 plus C2 natural log of x first. So the derivative of any constant is 0 plus derivative of C2 times natural log of x. It's just going to be C2 divided by x. And all that times x raised to the 1/3. and then plus, write all this down again. And now we just take the derivative of x raised to the 1/3, which would be 1/3 x raised to the 1/3 minus 1, which would be a minus 2/3. And of course here, I'll do a little bit of simplifying. Since it's not much, we'll just say this is going to be C2 times x raised to the 1/3 minus 1 here. So that would be the same as C2 times x raised to the negative 2/3. And then we'll rewrite everything else that we have. I'm going to keep this as is. All right, so I know that we can combine these two terms, but just to keep it simple, we're just going to leave it the way that it's currently shown. So now our first initial condition here is that y of 1 is equal to 1. So let's use this initial condition here. So this initial condition, we're going to use, I'm going to label these 1 and 2. We're going to use number 1. And so here, wherever I see x, I'm going to put 1. So I got C1 plus C2 natural log of 1. And this will be 1 raised to the 1/3. And all of that will end up equaling 1 itself. So here we see that natural log of 1 is just 0. And of course, 1 raised to the 1/3 is just 1. So all we really have here is that C1 is equal to 1. So we'll just go ahead and write that out. So our second initial condition is that y prime of 1 is equal to 0. So we'll go ahead and test that now. Y prime of 1 is equal to 0. And so here, I'm just going to write everything that we have here. So this will be C2 times 1 raised to the minus 2/3 plus C1 plus C2 natural log of 1. All that times 1/3, 1 raised to the negative 2/3. And all of that will end up equaling 0. And so now we just simplify. So here we know that 1 raised to the negative 2/3, that's just 1. Natural log of 1 is 0, so that means this whole term is 0. We already know that C1 itself is 1. And this 1 raised to the negative 2/3 is just 1. So switch back here. So therefore, what this means here is that we have C2 plus, and this is just 1 plus 0 here, so that's just 1 times 1/3, and that equals 0. And of course, this 1 times 1/3 here is just 1/3. So we see here that C2 would actually just end up being a negative 1/3. So therefore, our particular solution here will just be C1, which is 1, plus C2, which is a minus 1/3, natural log of x. And then, of course, x raised to the 1/3, or as I'm going to write it here, cube root of x. And so this will be our particular solution for this equation. All right, so we are going to conclude this video by doing a few case 3 examples. And remember that the case 3 example is the example where our indicial equation results in having roots that are complex conjugates. And so, of course, we have a special general solution that we automatically know what it is, and we derived it earlier at the beginning of this video. So we're just going to use it kind of like how we've been doing the other two. So for this equation here, again, we check the equidimensional thing out. And notice here that there is a missing y prime term. So this tells us that our a is going to be 4, but since the y prime term is missing, that means b is 0. And of course, c is the number next to y, which is 17. And we use that in our general indicial equation here. Plug everything in, and we see that we end up getting 4r squared minus 4r plus 17. Not something that we could factor out real easy. So we are going to use the quadratic formula. And so in using the quadratic formula, and notice that I'm using the quadratic formula once it's in this state. I'm not using it when it's in this state. Although I could have done that, the fact that I've actually plugged everything in, it's the equivalent of it. So we just use it in this form. So here we plug everything in, and of course you see after doing all the math there, you end up seeing here that we just get 4 plus or minus 16i over 8, and I just broke it up as 4 times 4i, because here I know square root of 16 is 16, and square root of negative 16 is 4i. And of course, this breaks up into complex conjugates, where this is my real part, 1/2, and 2 is going to be the 2i is going to be the imaginary part, where omega or w is going to be that corresponding constant for the imaginary part. So our general solution, we have x raised to the lambda times the linear combination of cosine and sine of omega times natural log of x, where the omega times natural log of x is the argument or inside of the sine and cosine function. So notice all we need to know is what is lambda, what is omega, and we just plug it in, okay? So again, this is our lambda, 2 is our omega. So we literally just plug in, going in the wrong direction. So just literally plug in what it is that we know, and it just ends up being the general solution, okay? And so here, notice that because I have natural log of x functions here, x here is going to be forced to be greater than 0, okay? Although I put it in this form here, it's still going to be that. Now, if you weren't convinced and you were saying, well, hey, I remember Professor Gant saying something about the absolute value of natural log of x. Now, that's very true. However, notice here that our lambda is 1/2. So what we see here is that we have x raised to the 1/2, which is the same as square root of x. And so having square root of x here forces you to have x values to be greater than 0 if you're going to produce real numbers for your result whenever you plug in values of x. So that's another reason why x would have to be greater than 0 for this particular ODE. Now, if you notice down here, I have gone ahead and taken the first derivative of this particular function, and I just used the product rule to do that. And the reason why I did it is because of the fact that we're actually going to use this later in, I believe, our last example here. Okay, and more than likely it's going to be an initial condition problem where we just use that information to figure out the constants. So, all right, so for our next case 3 example here, again, we see the equidimensional thing going on here. So we know that this is an Euler-Cauchy equation, our indicial equation. is just this. And here we realize that A is 1, B is -1, and C is 5. So therefore, our indicil equation just ends up being r squared plus -1 minus 1 r plus 5 is equal to 0. Here, this is just r squared minus 2r plus 5 equals 0. And for here, you can use the quadratic formula or do completing the square. This one is pretty easy to do completing the square on, so I'm just going to use that method here. So if I do completing the square, I know I want to force these first two terms to have a perfect square. So I would take whatever this number here is, which is -2, divided by 2, which is going to be a -1, and square 1, which is just 1. Okay, so I'm introducing this to force a perfect square here. But if I add 1, I have to subtract 1 as well to balance out what I'm doing with the completing the square method. So in doing that, I know that this r squared minus 2r plus 1 is just r minus 1 quantity squared. And I know that 1 plus 5 is a positive 4. And of course, from here, I will subtract 4 from both sides. And the fact that I have something squared equaling a negative number lets me know I'm going to get complex solutions here. And so I take the principal root of both sides. And I know that r minus 1 is going to equal to plus or minus 2i. Because of course, square root of a negative number is an imaginary number. And then I just add 1 to both sides here. And I see that these are my roots. And this is going to be equal to lambda plus or minus omega. And the important part for me is that lambda is going to be the real part, and omega is going to be the coefficient for the imaginary part. And thus from that, we know that our general solution here will be x raised to the lambda times c1 cosine of omega times natural log of x plus c2 sine of omega times natural log of x. And so all I need to do now is just substitute in my alpha and omega, or w if you want to call it that. And so alpha is just 1. So x raised to the 1 here will just be x. So I'll get rid of that. This will be c1 cosine of our omega is 2. So that's 2 natural log of x here plus sine of 2 natural log of x. And so this would be our final general solution for this particular ODE. So for our next example, this one should look a little familiar to you because we actually had this in example A. So we actually figured out what the general solution was for this particular ODE in example A. And we found that it was this, okay, this square root of x times c1 cosine of natural log of x squared. And this should have some parentheses around it here, and sine of natural log of x squared there. And of course, you could pull this 2 out of the exponent and just say cosine of 2 times natural log of x and sine of 2 times natural log of x if you want. Remember, we also had found the derivative already. And I don't know why this is not going steady here, but We had already found the derivative. So since we already have the general solution and its first derivative, all we need to do is just use these initial conditions here to figure out what C1 and C2 are. So that's what we are going to concentrate on here. So for our first initial condition, which is y of 1 is equal to negative 1, we see here that if we go ahead and plug in 1 everywhere where we have x and make everything equal to negative 1, then this will be minus 1 is equal to square root of 1 times c1 times cosine of natural log of 1 squared plus c2 sine of natural log of 1 squared. And this just tells us that negative 1 is equal to. Here we know that 1 squared is 1 and natural log of 1 is 0. And of course, same here, all this is 0. So this tells us that cosine of 0 is 1 and sine of 0 is 0, which makes this whole term 0. And of course, square root of 1 is just 1. So after all that simplification, we essentially see here we have 1 times C1 plus 0. So C1 just ends up being a negative 1 in this case. So we check out our next initial condition, which is y prime of 1 is equal to 0. And I'm going to write this one down here since it's a little bit longer. So here we have y prime of 1 is 0, and that's going to equal c1 divided by 2 times square root of 1 plus c2, or sorry, 2c2 times square root of 1. And all that cosine of 2 times natural log of 1 plus 2c1 square root of 1 here minus c2 2 times square root of 1, and all that times sine of 2 times natural log of 1. So here we know that natural log of 1 is 0. So that means that all this is 0, which means sine of 0 is 0. We also know that C1 was negative 1. So 2 times C1 is going to be a negative 2 here. We also know that square root of 1 is 1. 2 times square root of 1 is 2. Natural log of 1 is 0. So 2 times 0 is 0. And we know that cosine of 0, all of that is just 1. And again, here our C1 is just a minus 1. So we got minus 1 here. 2 times, and this is a C2 here. I will just leave that alone. We know that that's 1. We know that this is 2. And so now we just go and see what we got left. So we got 0 is equal to a negative 1/2 plus 2c2 times 1 plus, doesn't matter what this is here because all this is 0. And so what this basically tells us here, what this basically tells us here is that negative 1/2 plus 2c2 is equal to 0. which means that 2c2 is equal to 1/2. And of course, if we divide both sides by 2, we'll see that we end up getting 1/4 as an answer here. And so, of course, our C1 and C2 have been found. So we got C1 there, C2 there. And what we'll do here is write the final answer down here. So that means y of x. We already have what all this is going to be. So this will be square root of x here times C1. And C1 is just -1. All right, so I'll put the minus there for the -1. Let's go back up here. So that's C1 cosine of natural log of x squared. And then plus C2, which is 1/4, sine of natural log of x squared. So this would be our final answer here. All right, so let's move on to our last example. Oh, and I forgot to write here that, of course, x is going to be greater than 0. Again, because of that square root of x. All right, so now let's move on to our last example. All right, so for this example here, we do have a second order Euler-Cauchy equation, but we see that the initial conditions are a little bit more interesting than what we have been seeing. So I wanted to go through an example of this just to show you how to deal with situations like this when the initial conditions look a little crazy. So we start off all these the same. Of course, we see the equidimensional thing going on here with the y double prime term. We don't have a y prime term. So that tells us that in our integral equation that b is going to equal 0. And of course, we have the equidimensional thing going on in the y term because no derivative means order 0 for the derivatives, and 5 is the same as saying 5 times x raised to the 0. So that is of the degree 0 there. So this means our integral equation will end up being a times r squared plus b minus a times r plus c equals 0, where a is equal to 4, b is equal to 0, and c is equal to 5. So therefore, this means that we have 4r squared plus 0 minus 4 times r plus 5 equals 0. And of course, this means that we have 4r squared minus 4r plus 5 equals 0. And so for this one, I'm just going to elect to do the quadratic formula. So we'll say our two solutions here will be minus b plus or minus b squared minus 4ac all over 2a. And we are no longer talking about this a, b, and c anymore. We're talking about the a, the b, and the c here. Okay. So with that being said, we have a minus 4 plus or minus 4 squared minus 4a, which is also 4, and then c is going to be 5. And all that over 2 times a, which is 4. So we'll come here. So this gives us 4 plus or minus 16. And this is 20 here times 4, which is 80. All that over 8. And this will be 4 plus or minus, let's see, 16 minus 80. I know 20 minus 80 is 60, but then of course I got an extra 4 there. So this should be a minus 64. All this divided by 8. And since square root of 64 is 8, that lets us know that the square root of negative 64 is going to be 8i. All that divided by 8. And of course, we can split this up into real and imaginary part. And this will just end up being, hold on a second. So this will end up being 1/2 plus or minus I, or 1i to be more specific, which we will let be lambda plus or minus omega. So therefore, lambda is equal to 1/2 and omega is equal to 1. And so our general solution here, of course, take on this form. So the x raised to the lambda times linear combination of cosine and sine of omega times natural log of x. And of course, all we do is just plug in. So x raised to the 1/2 is the same as square root of x. And actually, I'm going to rewrite this as x raised to the 1/2 because it'll be better for us in finding the derivatives later. Got x raised to the 1/2 times c1 cosine of, since omega is just 1, we can just do natural log of x here, plus c2 sine of omega 1 is 1, so it's just natural log of x there. All right, so we have what our general solution is. If we go back to our initial conditions here, we have the actual solution here at a specific point, and we have the first derivative. So let's go ahead and take the first derivative of this function now so that we can use it later. So now that we have this, our first derivative, using the product rule, we will take the derivative of the first, which is just 1/2 x raised to the minus 1/2 times the second function, and then plus, we'll now have x raised to the 1/2 times, and now we'll take the derivative of both of these terms. So of course, we will have c1, and the derivative of cosine is minus sine. And then of course, the derivative of the inside function here is 1/x. We do the same thing again. We have c2, derivative of sine is cosine. And then multiply the times the derivative of the inside function, which is 1/x. So now that we have that, we're not going to try to simplify anything. We'll just leave it as is and just plug in what we need. So we need to apply our first initial condition. The first initial condition is that y of e raised to the pi is equal to 5. So here, first initial condition. So we're going to be using this equation here to do that. So this would just be 5 is equal to e raised to the pi, square root of that, and square root of e raised to the pi. I'll just keep it this way for now. Let's make it a little bit easier. So here, if I do e raised to the pi and all that's raised to the 1/2, that's just e raised to the pi over 2. Okay, so just keep it that way. And so here we'll have C1 cosine of natural log of e raised to the pi. And then this will be plus C2 sine of natural log of e raised to the pi. So looking here, we know that natural log of e raised to the pi, all of this will just be pi. And so this means that 5 is equal to e raised to the pi over 2. And cosine of pi will be -1. So this will be C1 times a -1 here, plus sine of pi is 0. So 0 times anything is 0. Thus, we see that we essentially have here that 5 is equal to minus C1 e raised to the pi divided by 2. And thus, this means that C1 is going to be equal to minus 5 divided by e raised to the pi over 2. And so we'll just leave it in that form for now. So we know what our C1 is. Now we need to find out what our C2 is by applying the second initial condition. And our second initial condition here is y prime of e raised to the pi is going to be equal to -3. All right, so of course, we are going to be using this second equation now. So y prime, that's just going to be -3, and that will equal, I'll come here, 1/2 of e raised to the pi. So let's get that right. E raised to the pi, and that raised to the -1/2 here, times C1, and I'll write that later when we need it, cosine of natural log of e raised to the pi plus C2 sine of natural log of e raised to the pi plus e raised to the pi times 1/2, which is going to be e raised to the pi divided by 2, minus C1 sine of natural log of e raised to the pi. And here, since both of these has a 1/x to it, I'm just going to divide by x, and of course x is still e raised to the pi. So it's going to make life a little easier there. Plus c2 cosine of natural log of e raised to the pi. Okay. All right. So this means here that we have -3 is equal to e raised to the negative pi over 2 divided by 2. And here, natural log of e raised to the pi, that's just pi. And cosine of pi is a -1. So here this will just be c times -1 plus c1 times -1 plus we got c2. And if you remember from before, natural log of e raised to the pi is pi, and sine of pi is 0. So all this is 0. Of course, all that is -1, that's 0. So here, that's just that times 0 plus. And so now we have e raised to the pi divided by 2 divided by e raised to the pi. That's the same as e raised to the pi over 2 minus pi, which is e raised to the minus pi over 2. Minus c1. And if you remember from here, sine of natural log of e raised to the pi, all of that is 0. So we're going to leverage that so that we don't have to keep recreating the wheel. So all this goes to 0. We know that all of this is just -1. So we see here, yes, all this is 0. So I'm going to erase that. So we got 0 here minus c2. All right, so now at this point, what I'm going to do here is multiply both sides here by a -2. And I'm going to do that so I can get rid of this fraction here. So if I multiply -3 by -2, I'm going to get a +6. If I multiply this by a -2, I'm going to get a minus e raised to the minus pi divided by 2. And everything on the inside here will stay the same. For this first term. For the second term, of course, if I multiply that by a -2, that's going to be e raised to the negative pi over 2. And notice here I have a negative c2 here, so a negative and a negative is a positive. So it'll be 2c2. All right, and so from here we see that we have a negative times a negative here. So that will give us a positive. Okay. And so now at this point, what I will do is, since we have common factors of e raised to the negative pi over 2, I will go ahead and factor that out. And what we have left inside of here is c1 plus 2c2. And so now from here, I'm going to divide both sides here by e raised to the negative pi over 2. Another way of doing that is just to multiply both sides here by e raised to the positive pi over 2. So I'm going to take that approach here. I'm actually going to write it out. Okay, so if I do that, then of course all this business here this is just another way of saying 1. And so what I have left here at this point is just 6e raised to the positive pi over 2 is equal to c1 plus 2c2. And so now I'm going to say, I'm going to solve for c2, and then I'm going to throw in c1 right at the end. So I'm going to have 6 times e raised to the positive pi over 2. I'm going to subtract c1 from both sides. And then, of course, to get c2 by itself, I will have to divide both sides by 2. So I will go ahead and do that here. And I'll just scratch this out for this step here. And this will end up being 3e raised to the positive pi over 2 minus 1/2 c1 equals c2. And here I'm going to go ahead and substitute in what c1 is. And if you remember up here, c1 was a -5 divided by e raised to the positive pi over 2, which we can alternatively express as -5e raised to the negative pi over 2. So I'm going to go ahead and do that here. And that's equal to c2. And of course, a negative times a negative here is a positive. So we see here we have 3e raised to the positive pi over 2 plus 5 over 2 e raised to the negative pi over 2. And so this will be my value for c2. So to kind of recap here, we found c1, and I'm just going to say c1 was this, make it easy. And we said c2 was what we found here. And so now we will just go ahead and finish up. So our general solution, y of x, and I'm going to just rewrite everything in general again. So if you remember here, general solution was just x raised to the lambda, c1 cosine of omega natural log of x plus c2 sine of omega natural log of x. So here, x raised to the lambda. If you remember, our lambda was 1/2, and our omega, or w, is just going to be 1. And I'm just going to write it like this for now, and then I'll put in everything else later. So that way we can just kind of look at everything all at once here. And I'll go ahead and replace this with lambda again. Right, so that is lambda. And I'm just going to record everything again. So remember, our lambda was 1/2, our omega was 1, and of course we already got what our c1 and c2 are. So therefore, this is x raised to the 1/2. Our c1, remember here, is -5 e raised to the minus 5 over 2, or pi over 2 rather. And that's cosine of omega is just 1, so that's just natural log of x plus C2, 3 times e raised to the positive pi over 2 plus 5 pi over 2 e raised to the negative pi over 2, and all that sine of natural log of x. And of course here, this x raised to the 1/2, if you wanted to, you could express it as square root of x, if you wish. So let's make sure we know that that's a 5. And that is it. I know it took us a while to get there, but this is our final particular solution for this equation given the initial conditions. And so this is the end of this example, and the end of this particular video with the study of Cauchy-Euler or Euler-Cauchy equations. I hope this helped. Take care.